So, guys, you are welcome to the day 30th of our MOST Academy exam preparatory class. Modern physics, radioactivity, and half-life, the last aspect of our modern and nuclear physics chapter. We only have one more chapter to go. Like I do say, apologies, because I'm still having issue with my YouTube page with respect to my Gmail. With time, I'm going to rectify that. So pending the time, we are posting videos on our Telegram page so that you guys can finish watching. We still have the semiconductor, which is the last part. And I just want you guys to help me recommend all my video series to students that you think are writing examination, because it will help them and also facilitate and enhances their score and also increase their pace in knowing answers to questions without any delay. So I will start with the solution to the aspect of radioactivity and half-life. You can also watch the full concept video on the YouTube page. If you have any doubt, you can direct them to my WhatsApp group, or you can also drop them to my mail. Like I said, this time around, it's no more functioning. But I've mailed a letter to them. I've written a letter and it shall be attended to soon. So the video concept here, it's just for quick revision. So let us start, guys, with the topic of modern physics chapter 3, radioactivity and half-life. The first question. Natural radioactivity consists of the emission of dash. I believe also in your chemistry, you might have studied radioactivity. It is just defined as the spontaneous emission or disintegration of nucleus. Basic facts, many of you have learned this in junior classes, spontaneous emissions of radioactive rays. So anyhow you call it, it's accepted. So it is always radioactivity, it's a nuclear process. It's a It's a nuclear phenomenon. Let me just write it like that, nuclear phenomenon. That is, it is only what it occurs or it emanates from the nucleus. It's a nuclear phenomenon, that is, it emanates from the nucleus. And I think it was I know, it was discovered by Henry Becquerel. That was the first man. Henry Becquerel, because of Waec student, Becquerel, in 1896. So when we talk about radioactive substance, it is taken from the nucleus. Now, there are a lot of laws and other things you can keep in mind, because later after Henry Becquerel, a lot of other scientists work on radioactivities. One of them is Rutherford and Soddy, Rutherford Soddy. Like I said, I don't want to teach you what is above your level, but you need to keep it in mind. Rutherford Soddy was able to tell us all what we've talked about here. That is a radioactive substance, X, can react to produce Y. So this is called the parent nuclear, and this is called the daughter nuclear. So now keep it in mind, Rutherford Soddy experiment or law let us know that what a radioactive substance is independent of chemical reaction. You can write that. I said a radioactive substance, Ra means radioactive element is independent, apologies to the spelling, of a chemical reaction. So like we say, they only emanate from the nucleus. Now, and another thing is, he also let us know that it is a spontaneous, because of theoretical questions like this, it's also a spontaneous reaction, that we cannot say out of a billions and millions of radioactive of the nucleus, or radioactive that is emanating from the nucleus, we cannot say categorically that this particular atom will be a radioactive element or this will be a radioactive element. It occurs spontaneously. Though there are ways in which you can produce, we can talk about artificial radioactive, which I'm going to talk about, series of radioactivity. That is a little bit of A level, but you can have idea because it will help you when you get to that level. So For now, let's limit it to with respect to what we have in front of us. So basically, you said it is from the nucleus of a radioactive substance. That is the definition. And when it is being produced in chemistry, you were told that it is basically from the lead chamber. For example, important points because of Waec student, something like this, lead chamber. Then you have the deflection, which is popular alpha particles, or you say alpha ray. The one that is not deflected says gamma rays, and this one is beta rays. So in chemistry, you talk about, and this is lead chamber. Lead chamber. If you like, you call it gigamolar Cantor. That is another word that is popular, gigamolar Cantor. All these are used to detect a radioactive substance. I don't want to go too much into what is not needed for questions. So from the nucleus of a radioactive substance, a radioactive ray of alpha, beta, and gamma have been what produced. Again, you can also keep it in mind. There is always a lot to talk about. You can also keep it in mind that each of them has what their own characteristics. In chemistry, you've talked about how you can detect alpha ray. For example, not to waste your time, alpha particle are more or less for your level. I will only concentrate on what is needed. Like I said, this is the way we write alpha particle. I say it's the same thing as helium atom. So I'm not going to talk more about other type of and beta particle, we write beta like this, we write is 0, -1, which you also understand. This is more or less like your neutron, you know that, like your electron. Now, listen, beta ray can actually what? We have three types. In A-level chemistry and A-level physics, we can have what we call beta positive, beta negative, and decay capture. I've talked about little about that if you watch the video series of nuclear physics, which was the first chapter on that structure of atom. Like I do say, don't worry, for your level, you don't have much. Then gamma remains same, it's not deflected, and that is 0, 0. So interpretation of this, not to waste your time. This is true. My two always look like alpha. Apologies for that. So basically, the question has been answered, but for future question, mass number 4 decreased by 4, atomic number decreased by 2 for alpha ray, for alpha particle, for alpha disintegration. Then the same for beta, and beta mass number remain the same. This negative means it's going to increase by 1. That is for the what? Beta ray, positive beta ray, the way you have been taught, which is the way your question will focus on. You are not going to talk about K capture of beta particle or what we call the negative beta ray. Don't worry about that. I'm not talking about positrons. When in your chemistry, you might have heard about positrons and nucleotides. Don't worry about all this. It is not needed for now. So let's answer the question. We have answered the question already, my dear students. Don't be tired. The answer to this is natural radioactivity emanated from what we call alpha, beta, and gamma. It may not be in order. It doesn't mean anything. But I think D is correct with respect to my explanation. That is the answer to that question. It's very, very simple. So we move to the next one. To see space, I'm going to clean this side. Now, the second question for today says, which of the following features is not a characteristic of natural radioactivity? I've talked about that. Let's see. It is a nuclear phenomenon. Yes, it occurs only in the nucleus. It is produced by the nucleus of a radioactive substance. Radioactive element is exhibited only by elements of mass number greater than 206. This is a lie. This is a lie. This is a lie. Let's make quick to explain to you what we call radioactive series. You need it just for the sake of your chemistry. Radioactive series. Now, in radioactive series, like I said, a radioactive element. Listen, guys. Radioactive element is the spontaneous emission or spontaneous distribution of nucleus. Now, if a parent cell is radioactive and it's going to give you after disintegration, it's also giving you a radioactive substance. Now, under the radioactive series, we have 4 categories, which you can keep in mind for now. We have the first one, we say thorium. Listen, when thorium is written as TH, I'll just help you out on basic. These are a little bit of chemistry. 90, that is atomic number, mass number is 282. That is the parent nuclear. When it's disintegrates, it's going to give you lead. Lead, generally, you know, lead is atomic number is 82, and mass number is 208. I'm talking about series. So S We can have X plus what else give you Y, Y also disintegrates to give you Z, like that, like that. You are talking about series of radioactive substance. Thorium is the parent element, then the daughter element, the way we call it in radioactive, is lead. That's the first series. We have first four of them. The next one is called neptunium. There's the first time to everything. If you've not heard about it, it's written as MP. Then we have 93. It's the atomic number. Mass number is 230. I hope I don't make mistake. I can't make mistake because all these things can be what derived mathematically. So, and that one, when it disintegrates, it gives a beta what a daughter nuclear of bismuth. I also have heard about bismuth. You know more about bismuth when we get to it. Semiconductors. So 83209, this neptunium is said to be artificial radioactivity. I will let you know a little bit about it. The next one is uranium. You guys know about uranium very well. Uranium is place is popular. Uranium is 92,238. And when this one disintegrates, it's also going to give you lead. But the lead you are going to have is also what we call 82. You can see. But this time around, it's not going to be 208, it's going to be 206. Then the last series of radioactive substance is what we call actinium. And actinium is also denoted by U as well. That is where something comes. That's chemistry for you. I'm going to shift this up here. Then you have actinium. That is 92. Then this is 232 as a mass number. So it's going to give you lead of 82, then 207. So in chemistry, basically, you call this one the series of radioactive substance, where this guy, I'm going to put in red, is called artificial. This is not real in nature. So these are series. In fact, we call this one 4n series, as this 282 is divisible by 4. We call this one 4n plus 1 series. We call this one 4n plus 2 series. And we call this one the 4n plus 3 series. The little you know, the better it gets. And these are the what? They are daughter element, or daughter nuclei, the way it is being called. Now, my point is, if you say radioactivity element exhibit, what radioactivity is exhibited, this is E, apologies, is exhibited only by elements of mass number greater than 2, as you can see. Now, radioactive element, this is all these ones are said to be radioactive. As you can see, this is not, it is not only by elements that is greater than 2. Please note that you can see all these apparent elements are also radioactive. And this is what you can see 206, greater than 206. We have lead is giving us 206.82. So if you say greater than 206, so this statement is incorrect. We can check others. The radioactivity of an element is affected by electric field and magnetic field. They are deflected. You can see they are deflected in what both electric and magnetic field. Then the last one, the radioactive element is transformed to a new. I just talked about it. You can see thorium gave lead, neptunium gave bismuth, uranium gave lead, actinium gave what? Lead. So this is what we call series of radioactive. It does not depend on what chemical properties. So chemical properties are different from what radioactive properties. Let that be known. More of that are discussed in your chemistry concept. But for now, I will limit myself to what is needed to the question. And I think I've answered the question. The answer to this is choice B. This is a question answer after statement that is not correct. So I'll move to the next one, my dear students. The next question is fine. The next question is, what is the neutron, number of neutrons in uranium isotope? Uranium is 238.92. That is 4n plus 2 series. We've talked about that now. We've talked about this under the other one. I think we've solved this question. I can't remember. So number of what we talk about an atom of X, we say if atomic number is Z and the mass number is A, the number of neutron is A minus Z. I think you still remember that this is atomic number of protons. This is mass number or number of nucleons. This is also called nucleons. So let it be known because those are ways examiner tends to take on it. Now, this here is a simple question. We just say neutron is 238. Apologies, this is not written well. The up one is 238 in this case, and this is 92. So you subtract 238 minus 92 to pick your answer. I don't want to talk too much on this. 238 minus 92 is going to give one of the options. I think 146. And the option to that should be choice one. The next question. The next question is, a radioactive sample initially contained N atoms. After 3 half-lives, the number of atoms that have disintegrated is that. Now, let's talk about this. We've talked about spontaneous emission of radioactive rays, spontaneous emission of what? Of nucleus, or disintegration of nucleus. Spontaneous disintegration of nucleus is defined radioactivity. When we define radioactivity, we define another important thing, which is important. We want to talk about measurement of radioactivity. Just listen to quick concept. When we measure radioactivities, we define an important phenomenon called activity of a radioactive substance. Now, the activity of a radioactive substance, very important, is now said to be proportional to the number of what active substance. I'll write that as N. Now, the question is, what do we call? I said the measurement of radioactivity. Now, the SI unit of radioactivity is DPS. I said DPS. DPS is called disintegration per seconds. Disintegration. Concept video available on my YouTube page. Disintegration per seconds. But this quick concept is going to help you a lot. Disintegration per seconds. Now, later I told you a lot of scientists work on what radioactivities. So one becquerel, I'll write as BQ, is the same thing as 1 disintegration per second, which is DPS, which is a unit of what? Radioactivity. It is not only that Rutherford and Soddy also work on what? Radioactivity. So we also have Rutherford's experiment, or Rutherford-Soddy experiment, or Rutherford-Soddy law. Now, Rutherford was the one that gave us the mathematical interpretation of radioactive substance. I hope my students are following. So my point is from here. Now, becquerel is also a measurement of radioactive element, which is the same thing as disintegration per seconds. Now, Rutherford also measure, we can say 1 Rutherford is equals, because disintegration per second is a very, very small unit. So it's the same thing as 10 raised to power 6 DPS. So that's another SI unit. So you can also measure radioactivity in form of what? Rutherford. And Madame Curie, I hope you have heard about Curie, the woman that discovered polonium and radium. I think you have studied that in your chemistry. Polonium and radium. Maria, she collected Madame Curie, Maria Curie, the way it is being called. I just call her Madame, don't mind me. Curie, I hope the spelling is correct. So the husband was even Pierre. Hope my spellings are correct. So I think they collected Nobel Prize for physics. Yes. Now that's another measurement which can also be used for measuring. We say 1 Curie Cu is equals to 3.7 times 10 raised to power 6 disintegration per second. So be careful for some examination question. I ask you for SI unit. Becquerel, DPS, Rutherford, and Curie are measurement of what? Radioactive element. So now we define radioactivity in terms of the activity, which is the measurement. And activity is what? The number of disintegration, just like DPS, per seconds, the N by dt. That is activity. Is now proportional to the number of active nuclei. N means the number of active nuclei. For quick one for A-level student, I want to know the derivation of this formula. You can always watch my concept video. So now, when we now introduce, I'm not going to derive anything. I just want to take you through how to get answers to some questions on half-lives, and I'll give you a quick method. That is what I'm known for. I solve question in a different way, so that it will be very, very easy for students to understand. I only want to give you not just formula, but how to come about it in some cases if you are asked to do so. Now, here you can now say, if the activity, which we call activity, I'll write this as AC, is number of disintegration of element or a radioactive element per second, is now proportional to the number of active elements or active nuclei. We call it nuclei, Nuclei. Now, from your mathematics, you can say the N by dt is now equals to, we now introduce a constant we call lambda L. This lambda L is another important phenomenon my student can keep in mind. This is now called decay constant. Decay constant. So let it be known, and this is how they come about decay constant. Now here you can now make lambda subject of formula. You can say lambda is now the N by dt. Look at here, I'll finish it here. Lambda, which is the K constant, is now equals to activity, which is the N by dt, divided by number of active nucleus. So this is why they will tell you that what the activity of a radioactive element, it's proportional to what? The decay constant, as you can see, and inversely proportional to number of active elements. So please keep this in mind. This is now called the n by dt over n is what's called disintegration per atom. Disintegration, I don't solve question, per atom. Very quick concept. You can always, because of some other questions that can ask you in terms of this. So this is now used to determine the stability of a radioactive element. Stability. I've done a quick concept also on my channel on how to prove this. So now this is what now led us to what decay equation. Now, you know, the rate at which element is disintegrating per second should be what? You can see, guys, the n by dt here now, here, the n by dt in this case now should be negative because element is disintegrating, it is going down. But we always write it in modulo form. You are not, this one, if you are used to my channel, modulo should not be a problem to you. Why we are putting modulo is because of some cases, because it's always negative, but we want to avoid negative values. We always put what? Modulo. Now, the stability of an element is what? Is the measure of its activity. Do you understand what I'm saying? So more stable elements will what? Disintegrate less. You understand what I'm trying to say? The one that is not stable will disintegrate faster. That is just it. Very simple to know. English, right? Fine. Now, that's not where we are going. This is now what leads us if I integrate both sides, which I'm not going to show now. I've done that on my channel. We are now going to come about the formula we call the decay equation, which was the mathematical proof of Rutherford and Soddy. Now, the mathematical proof, which is just what you need to know because of your exam, is that the number of what? Active elements, the number of elements that is left is equal to the number of active elements, that is n naught. I'm writing that as n naught now, e raised to power negative lambda. Lambda is what? Decay constant multiplied by t. This is very important, and this is what we call decay equation. Please, students should keep it in mind, decay equation. So this particular formula, I am going to ring it for you. I do say when I ring the formula, students need to write it in their short notes. I'm just trying to form a ring pattern. So this is now modified. Sometimes if you are given activity, you can also say activity is initial activity e raised to power negative lambda t. And the same thing is going for mass too. Mass is also equals to the old mass. E is exponential raised to power negative lambda t. So this formula is, lambda I said is what? Decay constant, and t I said is the time. Now, this will now lead us, well, from this equation, it now led us to an important topic you have done in your chemistry class, I am sure. That I am very sure. You talk about half-life. That is the total time taken for half of a radioactive element to decay, half-life. So from that, if we integrate this one, we say initial time at n naught, the time is what? Is small letter t. Then when the what? Substance has what? Reduced to half of its element, at that point we define half-life, which capital letter T is called half-life. So the time it takes for a radioactive element to decay to half of its origin, you can say half of n naught is n naught over 2. As at that time, it is no more called time, it is now called the half-life of that substance. Do you understand? So by that, if I integrate both sides again, which I've done on my channel, we are now going to get that what capital letter T is now equals to natural log of 2. Let me just help you write it, 0.693 over decay constant. This is also an important formula students can also keep in mind, because directly most questions we ask you to find half-life when decay constant was given. This is just the direct formula you are going to write. I told you when I ring formula, my dear student, please do what? Do write it. Now, this half-life formula has now been modified also in terms of mass and in terms of activity as well. So if we do that too, I'm going to run two other formula for you that will help you to solve a lot of questions. And that formula is now like a modified formula of half-life and decay constant. Now, the first one is now, if we have this equation now, in terms of half-life, my students should always keep it in mind. I always tell them, keep it at the back of your mind. Important, if it is in terms of what? We say the number of elements in terms of half-life, this particular equation, is also n naught. You can always follow my lead. I derive all these things on my channel, but you just need to write it for now, so that you can apply it whenever you have it. So n is equals to n naught, then open bracket 2 2 raised to power minus small t by capital T. Capital T, you know, is now half-life. If it's in terms of mass, it also works. The mass of the substance is equal to initial mass of active element 2 raised to power negative small t over capital T. Please, my dear student, write these two formulas down because it will help you directly to solve a lot of questions rather than use exponential, which will cause a lot of problems for most of you that you are not so good in mathematics. So it's a simple question. I'm just trying to let you see how we come about this, and some important formula I have actually linked, which you have to put down in your short note. Now, this is a simple question. A radioactive element sample, it's a radioactive sample initially contained n atoms. Number of atoms initially is this. After 3 half-lives, the number of atoms that have disintegrated is that. Now, there's a simple question. Answer is what? We said first one was 3 half-life. The first half-life is n by 2. The second half-life is n by 4. The third half-life is what? N by 8, which is the answer to the question. So after 3 half-life, it will be n by 8. You want to use this one, you can also use it. It doesn't change anything. Yes, you can use it. It does not change anything. So n, initial atom is n. So 2 raised to power minus t over capital T is what? After 3 half-life. That is 3t. 3t. After 3 half-life, that means capital T is equals to 3t. If you want to show mathematical skill, you can now say n equals to n naught. You don't need it. 2 raised to power negative t over 3t. As you can see, this gets cancelled out. I have n equals to what? N naught, open brackets, 2 raised to power negative 1 by 3. You know the meaning of this 1 by over 3. So it should be 1 over 2 raised to power 3. Everybody knows mass. And if you don't know mass, you can learn. That is the same thing as saying that it's same thing as saying that you have a 1 over 2 raised to power 3. I hope students remember the logic of indices. So here you can see that n is now equals to the initial one, n naught times 1 over what? Over 8. This is mathematical skill. But why do we have to have this formula? It will help us in some complex questions. These ones are basic questions you can do without wasting time. I hope you have seen the way I've done that. And that is exactly why I asked you to write all this modified formula to help you solve a lot of questions. So we move to the next point quickly. I want to solve all questions. I'm going to leave some for you as usual. Which of the following is true of the particle emitted in the radioactive disintegration? Fine. Alpha, beta, and gamma. We've talked about that. The alpha particle is a helium nucleus. This is very true. Now, alpha particle is helium. I've written that because, which is the answer. Other here will be wrong. The alpha particle is lighter than, this is wrong. It's lighter than beta particle. The alpha particle is deflected more than beta particle. You can see in the magnetic field, the beta particle is deflected more than alpha particle in that. Now, which of the following is true of particle emitted in radioactive? The alpha particle is the helium nucleus. Now, alpha particle is the same thing as helium. I think I talked about that. Remember that? Yes. Now, because helium is also written as 4-2. Please keep that in mind. Now, the alpha particle is lighter than beta particle. Is also true. I think this question is which of them is not true. This is also true. The alpha particle is deflected more than beta particle. Then I think this question, which of the following is not true? There's a typo error. Please keep that in mind because this is true. This is also true, but this one is not true. So please keep it in mind. That's the answer to the question. There's a typo in that question, which I have corrected. The next one, 8 alpha decays and 6 beta decays are necessary before an atom of uranium achieves stability. The final product in the chain has an atomic number of that. They didn't even tell us about uranium, but let's use the uranium that we know. I've told you about under the K series, under the series. Uranium is always 92. It should be given in your exam. On your exam day, you are going to have it. Uranium is 92,238. So it's a typo error from most the academic team. I'm sorry about that. So I hope it is that, but if it is not that, this is standard uranium atomic number. I hope students are following. So now, the next thing is there are 8 alpha particles. Alpha particle is written as 2 and 4. If there's 8 of this one, I hope you know what it means. So what that means is that I'm trying to cancel out what disturbing. That there are 8 of this, and there are 6 of beta. Beta we write as is 0, -9. You know what 8 of this means? That is decreased by 8 times 4. That is 32. 8 times 2 are 16 alpha particles. And this one, 6 times 0 is 2, will be what? Is 0. 6 times -1 will be what? -6. So let's do it one by one. So this guy is decreasing by 32 because 32 plus 0 is 32. So this guy is decreasing by 32. So 238 minus 32. And see what I'm doing? 238 minus 32, 86, 0. That is 206, which we already know, normal, it will be 206, 82, which is always when the final product of the stability of this, which I've shown before, but you just have to prove it. And that is what they are asking here. But for somebody that know what this guy will give you as a final product, as a what final element, is going to give you lead 82, 206. But let's see, this is a 16. 16 plus, we add this one. Please let it be known. We had this one. This is, you subtract 16. You subtract 16. This is 16. Then you add 6. When you subtract 16, it's just like saying 16 minus 6. 16 minus 6 is 10. I hope you understand that, 10. So you are just subtracting 10. 92 minus 10 is 82. Like I told you, it is 82, 206, which I've given to you under the what? The series of what? Radioactive substance. I gave you thorium, neptunium, uranium, and actinium. So the question only asks you for the atomic number. Atomic number is always written here. I hope you understand that, and that is how we talk about the answer to that question. So the next one, guys, we are almost through. So next one, my dear students, a substance has a half-life of 3 minutes. After 6 minutes, the count rate was observed to be 400. What was its count rate at 0 time? Let's write that. So we have talked about in terms of count rate or in terms of anything, and just write n equals to n naught, open bracket, 2 raised to power negative t over capital T. I hope students are following. So let's be careful. This is number of active nuclei. This is the number of that number of active nuclei. This is the number that is remained. So now let's see, guys. After a substance has half of 3, half lives. Typographical error is too much from this, my student, preparing the slide. Now we have half-life is capital T. It was 3. I'm going to write the parameter. After 6 minutes, after T equals to 6, the count rate was observed. That means the number that is left after 6 minutes is 400. So what was the initial one? That is n naught, is what you are looking for. So directly you can apply this my formula, which is also very good and quick. So n is 400. N naught is what you are looking for. You open a bracket, 2 raised to power negative t, negative 6 by 3. Everybody knows 6 divided by 3 is going to give you 2. That is 2 raised to power negative 2. 6 over 3 is 2. Let's do a little bit of math. I'll continue from this side. 400 is equals to n naught times 1 over 2 raised to power 2. Just what I did at the other time. 400 is equals to n naught over 4. N naught times 1, then 2 raised to power 2 is 4. So initial amount is 400 times 4, which is 1,600. So which will be the question answer? I hope you can see the way I've solved this without using any complex formula. That is why I asked you to link out to those formula, because my formula are very quick and it will really help you going forward. So the next question. About the next question, we have 4 grams of radioactive, that is mass. Now, material have half-life 10 days. Is spilled on the laboratory floor. How long will it take to disintegrate to 3.5? Technical question. We are dealing with mass. Mass is also the same thing. The mass that is left is the initial mass, open bracket, 2 raised to power negative small t over the half-life. Now, this time around, 4 grams. 4 grams, that is the initial mass. That is 4 grams. Then half-life of 10 days, capital T is 10 days. How long, that is small letter t, is what you are looking for, question mark. Will it take to disintegrate to what? 3.5. So that means the amount of mass that is remaining is what? Is 4 minus 3.5. It has disintegrated to 3.5. So the amount that is left is what? There is a 4 gram, then how long will it take to disintegrate to 3.5 of the material? So that means the amount that has disintegrated is 4 minus 3.5. That is what? 4.5 grams. So please be careful about this because that's the only technicality here. So substitute that in the formula, my dear students. We are going to have, I'm substituting here, M here is 0.5 is equals to M naught is 4, open brackets, 2 raised to power negative small t, you don't know, capital T was 10. So you can just do your maths any way you want it. Look at this now. It's 0.5. I can do it faster than this, but let me take step-by-step method. 4 open brackets, 2. You can see I can just turn this 2, just like what I did here. You can see I dealt with this 2 raised to power minus 2 as 1 over 2. You can see 1 over 2 raised to power 2. So this 2 raised to power, this one, I can also deal with it by saying 4 times. I just want to follow the same method. 1 over 2. I want to cancel the minus t over 10. So what I have here is a 0.5 is equals to 4 times 1 is 4 all over. I'm just showing step by step 2 raised to power t over 10. You can cross multiply. Then you have place. Let me continue here. Is 0.5 multiplied by 2 raised to power t over 10 is equals to, I have multiplied this by 4. So cancel 0.5, I divide both sides by 0.5. I'm showing you step by step because some of us are not that good in maths. Divide by 0.5. 0.5 cancel 0.5. 2 raised to power t over 10 is equals to 4 divided by 0.5. I think should be 8. 4 divided by half is 8. So you can now use your indices. 2 raised to power t over 10 is equals to 8 is 2 raised to power 3. From indices, they will say this will cancel, then you equate the power. So t over 10 is equals to 3. What is t? Cross multiply. T is 10 times 3. That is 30 days. And that will be the question answer. So guys, you can see how the formula is working, and I think it's better for you to add it to your formula note. So that's the answer to this question. So we'll go to the next page. The next page says, which of the following are true of alpha decay? And mass number decreased by 4 alpha particles. Atomic number decreased by 2. This is correct. This is correct. Mass number does not change this one. So answer is 1 and 2 because we have talked about it. After 3 half-life, the fraction of radiant element that has decayed, you can see this is quite different from the other one. After 3 half-life, the number that has decayed is the first one is n over 2, the next one is n over 4, the next one is n over 8, which we have taught. So they said the fraction of elements, so initially there was n. The fraction of element that has decayed. So if this is the amount of elements that is remaining after 3 half-lives, the number that has decayed will now be n minus, just like what I did, n over 8. So which is 7n over 8. So we are looking for a fraction. The answer is 7n over 8. So keep it in mind. If you use the formula, we are going to get the same answer. We are going to get n over 8. So they are asking you for the amount that has decayed. This is the amount that is left. N over 8 element is left. So we are looking for the amount that has decayed. That is 7n. The initial amount was n. So minus the amount that was that is remaining. We give you the amount that has decayed. So that's that about that. Be careful about all those subtraction things. And I think that is all for now. Or we should have one more page. Okay, fine. The last page. The activity of a radioactive substance depends on, I've talked about that the other time. I never mentioned what activity I say is dN by dt. I said it's proportional to the number of active nuclei. Then when we introduce constant, the constant was now what I call what? The decay constant. So temperature does not affect the activity of the substance. So temperature is not of answer. So anything that has temperature, you cancel it. So the answer that you have left is what? Age and purity. Age is the time. You know, as you get aged, that means the time in year is increasing. Then purity, we have different type of substance. Pure substance, stability is high. Impure substance, stability is low. So activity is the measure of stability. Purity is also a factor, and that is why we are picking this as our answer. So guys, the last question, I will leave it for you guys to do. Which of the following is most strongly affected by magnetic field? Either magnetic field or electric field. We know gamma is not deflected. Alpha is positive, beta is negative. So I've said the answer. You can pick it and drop your comment on the comment section when you have it posted on YouTube. For now, it is going to be posted on our Telegram page. So, guys, if you find anything interesting, kindly subscribe to our YouTube channel, please, and share the video with your friends. And another thing is the best way to learn all this is to watch all the series of the video. Thank you, guys. We'll see you soon with the topic of semiconductor. Bye.